At first glance, these are all wingers, or more generally, wide players. They influence the game from similar areas of the pitch, but if you actually watch them play, you know they're doing very different jobs. Some stretch the defense, some drift inside and create, some progress the ball, some live in the half spaces. So the question is, can we systematically define different types of wingers using data? In this video, we're going to use an AI technique called k-means clustering to do exactly that. Instead of relying on labels or opinions, we let the data decide which players are actually similar and which ones aren't. What you're looking at here is a scatter plot of many wingers across Europe. Each dot is a player, and the position is determined using something called Principal Component Analysis, or PCA. Once we project players into this space, something interesting happens. Without telling the algorithm anything about positions, names, or roles, it naturally separates wingers into four distinct groups. Each color represents a different type of winger, defined entirely by their statistical profile. Now, watch what happens when we bring our example players back into the picture. Each one lands cleanly into a different cluster, not because we forced it, but because their on field behavior genuinely differs. This is data revealing structure that matches what we intuitively see on the pitch. And we can push this idea even further. By adding one more principal component and moving into three dimensions, we start to uncover subtypes within each group. Players who look similar on the surface but contribute in subtly different ways. Now let's zoom in and look at how the clustering itself actually works. Here, each point represents a winger plotted using just two metrics: expected goals per 90 and expected assists per 90. For now, we'll keep things simple and work in two dimensions. We'll talk about adding more metrics later. The algorithm we're using is called k-means clustering. Its job is simple: find the players who are the most similar to each other and group them together into what we call clusters. Similarity here is defined purely by distance. Players that are closer together in this space are considered more alike. If you want to know more about similarity, watch my video on this topic. K-means starts by asking one question: how many clusters do we want? Once we choose that number, the algorithm places a set of central reference points, called centroids, at random locations. These centroids act like anchor points for potential groups. Next, every player is assigned to the nearest centroid. Whichever centroid a player is closest to, that's the cluster they belong to. So, after the first assignment, we update the centroids. Each centroid moves to the average position of the players currently assigned to it. With the centroids updated, we repeat the process. Players check again which centroid they're closest to, clusters update, and the centroids move again. This loop continues until nothing changes when players stop switching clusters. At that point, the algorithm has converged. We're left with stable groups of players who are genuinely similar based on the data we gave it. In this simple example, these groups naturally line up as scorers, passers, and hybrids. But the key idea is this: the algorithm wasn't told what those labels mean. All it did was measure similarity, and the structure emerged on its own. As we can see here, these example players broadly fit the cluster they're assigned to, but grouping players using only these two metrics is still too coarse. To really understand why these players are different, we need to look at the underlying metrics that actually define their roles. So let's take a step back and talk about the features we're clustering on. To really tease out the different types of wingers, we need to look at many dimensions of performance, not just one or two stats. First, we have scoring and attacking threat, metrics like expected goals, expected assists, and shots per 90. These capture how directly a winger contributes to goal scoring. Next is creativity. Key passes, shot creating actions, and goal creating actions tell us which players are responsible for turning possession into chances, even if they're not the ones taking the shot. Ball carrying and one versus one threat. Progressive carries, carry distance, and take ons measure which players consistently move the ball forward and destabilize defense on the dribble. Finally, we have positioning and width. Touches in the attacking third, touches in the box, and crosses help distinguish players who hug the touchline from those who drift inside or attack central spaces. Now, here's the problem. This is already a lot of information, far more than we can realistically visualize at once. When we previously looked at just two metrics, like XG and XAG per 90, we were only seeing a very small slice of the full picture. At best, we can add one more dimension, for example, progressive carries, and move into three dimensions. But even this barely scratches the surface. We're still ignoring most of the information that actually defines how these players play. In reality, each player exists in a much higher dimensional space where every metric adds another axis. So, how do we reduce all of this complexity without throwing away what makes players different? That's where principal component analysis, or PCA, comes in. PCA finds new directions in the data that preserves the most important differences between players, allowing us to compress many metrics into just a few meaningful dimensions. Let's look at a simple example of how that works. Let's start with just two metrics: carries on the x-axis and live passes on the y-axis. Even with only two stats, K-means already finds three sensible groups: low, medium, and high involvement players. But notice something: the points almost fall along a line. That's not a coincidence, it's a sign these two variables are strongly correlated. Players who carry a lot also tend to play a lot of live passes, and players who do little of one usually do little of the other. So, in a way, these two dimensions are giving us overlapping information. We don't need both axes to capture overall involvement. We can summarize it with just one number. One obvious idea is a weighted combination: carries plus passes, with weights that decide how much each metric matters. That's the core idea behind a principal component. A principal component is really just a direction through the data, and we choose the best direction by asking which line captures the most spread when we project the points onto it. As we rotate the line, watch the spread change. Those little yellow segments are the projections, each point dropping onto the closest point on the line. The direction where the projected points are most spread out, that's PC1. Once PC1 is fixed, we can find a second direction, PC2, that must be perpendicular to PC1. PC2 captures the biggest remaining variation that PC1 didn't explain, and together they both represent 100% of the variation in this two metric example. So we've essentially just rotated our coordinate system. So instead of viewing players as carries versus passes, we rotate the axes so the data is described by PC1 and PC2. Now, here's the punchline. If we collapse everything onto PC1, essentially ignoring PC2, we can still separate the players into clear groups. So we reduce the dimension from 2D to 1D without losing the structure we needed for clustering. And PC1 isn't magic, it's just a weighted sum of the standardized metrics. We standardize using z-scores, so metrics on different scales don't distort the results. In this case, both weights are positive, so PC1 is basically measuring total carries and total pass volume. For example, this player has a z-score of about 2.7 in carries and 2.17 in live passes, and those contribute together and give you a PC1 score of about 4.87, which is why they sit far to the right. Now that we've gathered all the winger metrics we've talked about, we can compress them using PCA and then run k-means clustering on that PCA space. And this results in four groups that the data naturally separates into. Before we talk about the clusters, we need to understand what these axes actually mean, because PCA axes aren't shots or dribbles directly, they're weighted mixtures of all the stats. We can see here that PC1 and PC2 are affected by the following metrics, and let's drill down into PC1 to actually see exactly how. We can see that the most influential metric in PC1 is attacking third touches with a weight of about 0.36, followed closely by carry distance at 0.34, shot creation at 0.33, and so on. Because all of these weights are positive, increases in touches, carry distance, and creation all push PC1 higher. So, players with a large positive PC1 are wingers who are constantly involved, getting touches higher up the pitch, progressing play, and repeatedly showing up in attacking sequences. And players with lower PC1 values are simply less involved in those progression and creation moments. Doing a similar analysis for PC2 allows us to create a simple interpretation of the principal components. Moving right on PC1 means more progression, more involvement, and more creation, while moving left means less of that. And PC2 is more of a style axis. Higher PC2 leans towards scoring threat and box presence, while lower PC2 leans toward more wide play and crossing behavior. So, with just these two axes, we already have a pretty readable map of winger behavior. Now that we've talked about what the principal components represent, let's drill down into each cluster. Let's start with the superstars. These are the players who combine high involvement with real end product. They're dangerous because they can both create and finish at elite levels. This is seen by the fact that they have large values for both PC1 and PC2. And you'll recognize most of the names here immediately. Mbappe, Dembele, Lamine Yamal, Rafinha. The model is picking up exactly what we'd expect. These are the elite players, and they belong to a group of their own. As a note, you'll sometimes see a player that you would call a striker in this list. And in the modern game, wingers and strikers have kind of blended. And so if a forward does enough wide actions like take-ons, touches high up, and crossing, then they behave like a winger statistically. And I've included them in this analysis. Next, we have the attackers and box finishers group. These guys rate strongly on the shooting and box touch side, but they don't pop as much on the passing and progression profile. So they look more like direct attackers, get into dangerous areas, take shots, finish chances, rather than being the main progressor or creator. Next, we have the progressors and crossers group. Basically, this is the opposite of the previous group. These players drive the team forward, carrying, progressing, and often creating danger through wide delivery. They might not be the highest pure shot volume players, but they're constantly moving the ball into threatening zones. Finally, we have the system role players. They aren't extreme in any one direction compared to other clusters, which usually means they play a very specific role in their team's structure. They're still valuable, they just don't dominate the stat profile in the same way as the others. One more key point is that PC1 and PC2 already explain about 60% of the total variation across all the metrics that we looked at, which is kind of insane considering we started with more than 10 dimensions. But if we want to tease out more nuances inside each cluster, we can add one more component, PC3, which explains roughly another 12%. And remember, PCA plus K-means is unsupervised. This isn't the one true set of winger types. It's the cleanest structure the stats reveal. Now, watch what happens when we introduce PC3. Same exact players and PC1 and 2, but now they lift up or drop down depending on their PC3 score. So PC3 is capturing new behavioral splits that PC1 and PC2 couldn't fully explain. Now, if we look at the PC3 loadings or weights, it makes this component quite interpretable. On the positive side of PC3, the biggest weights are box touches, dribbles attempted, and attacking third touches and carry distance. On the negative side, the biggest weights are XAG, goal creating actions, shot creating actions, key passes, and crossing trends. So, an overall summary of PC3 would just be that it splits up dribble to box threats versus final ball creation type players. To drive this point home, let's look at an example of how we can use PC3 to explain differences inside the superstar cluster. Note that Mbappe and Lamine Yamal sit higher up on PC3, which suggests a profile with more dribbles, carries, and penalty area involvement. Meanwhile, Dembele and Rafinha sit lower, which suggests a profile that's more about the final pass and actions that directly set up goals. So we can see how PC3 can reveal different styles within our superstars. Some are more carry and dribble into the box, and others are more unlock the defense with the final ball. And that's the end of this video. I know we covered a lot, and I hope it was very informative and helpful to you all. Please let me know in the comments if you have any questions or suggestions for a further topic. Thank you all so much for your time and attention. Have a good one.
Come on. Yeah, okay, see. Yeah. Yeah, P knocking like the rock up in the pie. Baby mama gonna pop it while you lie. Look back at it while I'm looking through these eyes. Lot of options and we buying out the lies. I remember shopping at the big lies. Now it's every day we need a bigger lie. Turn the loop, get to fucking up the hives. Lose your mode in the 3 kingdoms.